All right, so again, just to quickly remind you guys that in Biochem 2, we're very interested in understanding metabolism, and basically what this is we're going to study how these biomolecules get degraded, get synthesized, okay? And the first topics to almost all Biochem 2 courses will be glycolysis, okay? In glycolysis, we're interested in knowing how glucose, and you saw last lecture about where we get glucose in our daily diet, okay? You get glucose from starch, you get glucose from sucrose, like the sweet drinks that you drink. For some bacteria, you also get glucose from cellulose, okay, that kind of places. And glucose is really a very abundant sugar in the world, and because of that, biology or biological organisms have evolved to utilize glucose. Now, the overall reaction for glycolysis is glucose plus 2 ATP, and you have seen where we use the 2 ATPs. Okay, in the first reaction, hexokinase, and in the third reaction, phosphofructokinase. Okay, so in those two steps, you use ATP to sort of activate the sugar and allow it for further reaction. And at the end of the day, you will get to pyruvate, and just so you know, pyruvate is like the center of metabolism. If you have pyruvate, you can produce whatever you want, okay? Also, when you get a pyruvate, you will generate 4 ATP and 4 NDH, okay? So this is the overall reaction of glycolysis. And obviously, you can see that the 2 ATP can be crossed out, and you're left with just 2 ATP at the end, okay? So this is the net reaction of glycolysis. And we talked about reactions 1 through 3 last lecture. Today we're going to finish up on the glycolysis reactions and mechanisms, and we'll very quickly get to what happens to pyruvate and how to synthesize glucose, okay? All right, as you can see over there on the screen, for reaction 4, this thing is called aldolase, and remember that the name is derived from aldol. It's an aldol reaction, okay? Back in lecture 1, we talked about when you have a deprotonated alpha carbon, okay? And that alpha carbon, if reacts with a aldehyde, you will form a aldol product, okay? It's an aldol reaction. And in this case, aldolase does exactly that, but sort of in reverse, all right? So aldolase, essentially, it catalyzes a reversible aldol reaction. All right, and the two products are shown on the screen, one being dihydroxyacetone phosphate on the left, and the other one is glyceraldehyde 3-phosphate, okay, where glyceraldehyde is the aldehyde, and dihydroxyacetone is the ketone or the carbonyl that will have a deprotonatable alpha proton, okay? So when we have the aldolase reactant, and then OH, proton, OH, so the substrate for this reaction is fructose 1,6-bisphosphate, right? And then obviously the end product is 3 carbons and 3 carbons, right? So it's 2 3-carbon molecules. So obviously, you know, we're going to somehow get rid of the bond between carbon 3 and carbon 4. Okay, so that's what we're going to do. Now, turns out for aldolase, there are 2 types of aldolase. I'm going to talk about the first type, sort of. The first type, it's simpler in a way, so that I'll show you how it's done. All right, so I think this is called type 2. It's probably not in your book. This is primarily found in bacteria. Okay, it's an easier mechanism, right? So in this type of enzyme, you have a zinc ion, okay? You have a zinc ion right there. And zinc 2 plus sort of serves as a electron withdrawing effect, okay? So you have a electron on the carbonyl oxygen will be drawn to zinc 2 plus, okay? So obviously you sort of have some kind of stabilization here, electrostatic interaction. Now, I'm very interested in somehow getting rid of this bond, okay? So it turns out you have a general base. It's going to pull this proton away such that the electrons is going to jump to the oxygen, okay? Once it jumps to the oxygen, it jumps to form a carbonyl right here, okay? Now this particular carbon, carbon number 4, would have too many bonds, right? Because the base pulls the proton away, and the electron is going to jump to form a pi bond between the oxygen and the C4 right here. And the C4 now has too many bonds, so one of the bonds is going to go up, like that. And then once it goes up, now your C2 will have too many bonds. Okay? So the electron on C2 is going to pop over to the carbonyl, like I showed. So then, when the 2 electrons from here pop over to C2 and C3, this bond is then erased. Okay, this bond is gone. So now you have a okay. This is glyceraldehyde 3-phosphate. Okay. And then the other product is now looking like this. Okay? Now it looks like that. And this oxyanion is stabilized by the zinc 2 plus. Okay, so that's the reason why you can do this. You need to have an electron withdrawing mechanism on the carbonyl so that it can sort of attract the electrons moving towards that general direction. And then, remember you still have your enzyme base with the proton. Okay, now this guy right here, the electrons right here. Okay. Will sort of grab this guy, and this guy comes back down. Okay? So that the charge on the oxyanion, remember, it can only do 2 things. Either it grabs a proton, or it comes back down and to form another bond with carbon. Okay? Then, when it does that, you regenerate the carbonyl. And then okay, and this is DHAP, dihydroxyacetone phosphate, because it has 1 carbon, 2 carbon, 3 carbon, and acetone is the thing in the middle. Okay, so it's like that, and then the 2 hydroxys, and then that's the phosphate. Okay. All right, does that make sense? Or you can just look at that. That works too. All right, so basically in aldolase reaction, you have some kind of electron withdrawing mechanism right here. That's sort of the most important part. Okay? So because you have an electron withdrawing effect, then that makes your electron able to sort of pop over to the carbonyl, and your carbonyl becoming a oxyanion or enolate actually. This enolate will become stabilized, okay, and then you can finish your mechanism there. Okay, so this is type 2 aldolase. I think reaction is, the mechanism is relatively simple. But obviously you have to understand that you want to break bonds between C4 and C3 because you want to break this bond. You need to let the 2 electrons on here go away, okay, go somewhere. Okay, we're good? So can I erase this? It's on there. So if you copy, it's on there. It's on the first part. It says type 1, or type 2. 有没有问题? We're good with this? It's not too bad. All right, so aldolase, it's the first reaction that cleaves your sugar from 6 carbons to 3 carbons. Okay, so 2 3 carbons. So it goes from a hexose to 2 triose. Okay, well, triose phosphate. Now, type 2, I usually talk about type 2 first. That is because type 2 mechanism is easy to understand because you have a zinc that stabilizes it. However, in humans, we use type 1 aldolase. So we have type 1, okay? And this is found in like humans and stuff, or higher organisms. And same thing, I start with okay, I start with my fructose 1,6 bisphosphate. Okay, this is where I start from. And okay, instead of having a zinc there, turns out what we're going to do is we're going to have a enzyme that has a lysine. Lysine has NH2 as the R group, right? Lysine has NH2 as a terminal amino group on its side chain. And what this guy is going to do is it's going to the lone pair electrons on the nitrogen attacking the carbonyl center. This guy goes up, okay, and you will temporarily form this thing. This is carbon, O minus, CH2, OPO3, okay, and down here, OH, like that. Okay. For now, I'll just say the rest is R. Okay. And obviously, oxyanon is going to do something. Okay, it's going to do something, and essentially, what it's going to do is it will grab a proton, like this. Okay. Okay, so you deprotonate this guy, and then you transfer the proton from the amino to the hydroxyl group. Okay. Now, turns out there are lone pair electrons on the nitrogen again, and what this guy can then do is comes down and form another bond. Okay. And now this carbon will have too many bonds, so the electrons is going to pop to the oxygen. Okay, and essentially the oxygen electron then can then grab this guy. Okay, so at the end of the day, what you get is a shift base. And double bond. This is the carbon and CH2O phosphate, and then OH. Okay, this thing is called a shift base. Okay. Here's supposed to be a hydrogen, so if this hydrogen is here, so I'm just gonna, let me erase this real quick, and let's just say I'm going to grab a proton in the solution. okay, such that you leave this with a positive charge. Okay. We'll need that a little bit later. Yeah. All right, but the bottom line is you generate this particular structure. Okay, so you generate this shift-based intermediate, and that is attached to your enzyme. So now, okay, so essentially you turn your fructose 1,6-bisphosphate, the carbonyl, into your imine. Okay, so double bond O becomes double bond N. Okay, so that's a shift-based formation. So you use a amino group. You use an amino group to sort of replace the oxygen, kind of. Right. So you form a shift base here. All right. Now, then what this enzyme can do will be very similar. It's going to grab this proton. Okay, so somewhere on the enzyme, you have another basic residue, and it's going to grab, or general base, you're going to grab the proton, and the electrons are going to go to the oxygen, okay? And the oxygen electron is going to come back down to form the carbonyl, and the bond between C3 and C4 pop up, okay? And now this guy has too many bonds, so one of this bond is going to pop over here, okay? All right, does that make sense? Now, the shift base also serves as a electron withdrawing group because your amine or your nitrogen is positively charged, so that's why I fixed it. Okay, it's positively charged, so it's going to withdraw electrons towards it, such that you form CH2O phosphate, and you have one bond NH, one bond enzyme. Okay, and now this guy becomes double bond OH, H, and this one becomes your okay, so this one is already glyceraldehyde 3-phosphate. Okay, so glyceraldehyde 3-phosphate, it's already the direct product when you do the bond breaking mechanism. Okay, now, so G3P is free. Now you have to liberate the DHAP. Okay, obviously you can imagine where the lone pair electrons coming back down. Okay, and then remember back somewhere we had a BH plus. Okay, this one is going to grab this proton. The electron goes back to the base. Okay, and you generate that. Okay. All right, so then you have to somehow get the DHAP back from this shift base. Okay, so you already generated your hydroxyl group here. Okay, and your here the carbon with the phosphate doesn't change. So all you have to do is then get rid of this thing, replace it with a double bond O. Yeah. Okay. Turns out the mechanism is exactly reverse of what I just showed you with the shift-based formation. You have a water somewhere, okay, so you have water somewhere, and water can attack this, okay, and then the bond can go here, right, and then gradually you deprotonate the protons on the oxygen, and then you will be able to kick out your nitrogen, okay. I have no idea. I thought someone had a question or something. Okay. All right. So I'm not going to redraw the shift base formation mechanism. Okay. I think it's there. Okay. Or what I can do is post this. It's essentially this. Okay. This is the shift base. Okay. And that's the water. And what you can do is N double bond C here attacking this carbon, forming an OH2 kind of. Okay. And obviously one of the protons will leave as this one comes back down, okay? And then you form this general structure of a tetrahedral intermediate. And then what this guy can then do is you can have the electrons from the oxygen coming back and form a carbonyl, and the electrons of this entire group leave, okay? So it's just the reverse of the shift base formation. Then, so after reaction 4, we have generated our 2 triose phosphates. Okay, so one of them being DHAP. So this then becomes with water pumping in, and you would generate OH. Okay, so DHAP. DHAP. Okay. Now, since you have 2 triose phosphates, okay, you have G3P and then you have DHAP. Okay. Now, think about this as if you were doing sort of like a evolution or a design kind of thing, where now you have 2 types of trioses. Okay, and I give you a question of, I want to convert these trioses down into pyruvate. Okay? There are 2 ways to do it. Okay? The first way is to sort of, you make DHAP become G3P or G3P become DHAP, and then use one pathway to go down to pyruvate. Okay? That's one option. The other option is you design 2 types or 2 independent pathways, one for consuming G3P and one for consuming DHAP. Okay? So you have 2 options. And obviously, through evolution, we want to sort of minimize the amount of redundant pathways or unnecessary reactions or unnecessary enzymes. So evolution favored the sort of production of this isomerase that could then convert G3P to DHAP or DHAP to G3P, and then use one set of an enzyme that can convert G3P down to pyruvate. Right, so this thing is called triose isomerase. Right? Triose isomerase. That's right. Okay? So triose meaning 3 carbon sugar, isomerase, it's that it's doing a isomerization reaction. Okay? You have you want to convert DHAP to G3P. DHAP looks like this. Okay? Acetone, dihydroxyacetone, dihydroxyacetone phosphate. And it's going to convert that into glyceraldehyde 3-phosphate, which looks like this. So if you look, obviously you notice that the phosphates sort of here, they don't really change. Okay, so phosphates don't change. Okay, so this carbon, essentially this carbon doesn't change. And what really changes is this. Okay, you move the carbonyl from C2 to C1. Okay, right, so here C2, I don't even know if you call this C1, but you're moving the carbonyl from this carbon to this carbon, okay, such that it then generates an aldehyde and a hydroxyl group on the C2. Now, the mechanism, okay, the way it works. Okay, so mechanism. This guy is OH, OP, PO3. Now, you have an enzyme that has a base. Enzyme that has a base, okay, so it's like everywhere. What it's going to do is it's going to attack the alpha hydrogen. And alpha hydrogen is deprotonatable because it can form an enolate like that. Right? So if I pull away the hydrogen as a proton, then the 2 electron here has to go somewhere. So the 2 electron here go and form a new bond between the alpha carbon and the carbonyl carbon. Okay? And the carbonyl carbon, now one pair of the electron between C and O has then go up to the oxygen. Okay? So then you generate, and by the way, this is all reversible. You then generate this enolate intermediate. Okay, this enolate intermediate, enolate, okay, so enolate, okay, enolate intermediate. Now, what do you suppose happens next? If you want to get this guy to become this guy, what do you suppose will have to happen? Seeing that the C2, the oxygen on the C2 now becomes an OH, so that means what? It's going to grab a proton somewhere, right? Turns out this guy can simply grab this proton and the electron here. So then you can generate this intermediate where now you have OH, O minus, H, OPO3, okay? Like that. So once you once you do this reaction, then what you get is this, right? So you just transfer the proton. Okay, you transfer the proton from one OH to the O minus. Now, when this O minus, this electron, it can come back down, okay? Because you want to form an carbonyl right here. So you, by looking at the final structure, you should be able to guess what the mechanism would be like. And when it does that, now this particular carbon will have too many bonds. So then what it's going to do is the 2 electron here is going to grab the proton that was on the enzyme, and then like that, okay? So then at the end, what you'll get is okay? Does that look like that? I think so, right? Just a little awkward. So 3 carbons. The first carbon is a carbonyl, so it's an aldehyde. And then second carbon is a hydroxyl group. And then the third carbon is a phosphorylated hydroxyl group. Okay, so it's phosphoryl. Okay? Does that make sense? Okay, so now you can see that we can then generate DHAP. So this is the DHAP to then G3P. Where have you seen this mechanism? Phosphoglucose isomerase, okay? This one is a triose isomerase, so you can have a hexose isomerase, so sugar isomerase turns aldols to ketols, ketols to aldols, right? So all isomerase, at least for this type of reaction, will look like this, okay? So the mechanism are the same. So reaction, this is what, like reaction 5? So reaction 5 mechanism is the same as reaction 2 mechanism, right? Do you guys remember? All right. So now we have generated G3P. Essentially, we finished the investment phase. Okay, so I go from glucose down and I produce 2 G3P. Okay, and in the process, I used up 2 ATP. Okay, so this is the investment phase. Okay, so after the investment phase, I'm going to start to get some return. Okay. All right. Okay, so the next reaction reaction 6. This reaction is catalyzed by this enzyme called the glycolaldehyde 3-phosphate dehydrogenase. Okay, so you know that this one is a dehydrogenase, so it's an oxidoreductase, so it's going to do electron transfer. Okay, electrons have to go somewhere. Right? Now, I will start with, let's see how I draw this. Okay, I start with my glycerol aldehyde 3-phosphate. Okay, this is G3P. And my end product, okay, my end product is going to be something that looks like this. Okay, what changed? So you just look at the reactant and the product, and you first thing you look at what changed. Okay. So initially you started with an aldehyde, and at the end you have a phosphoester. Okay, so it's a phosphate ester. So remember that phosphate ester has the same oxidation state as an acid. Okay, so you go from aldehyde to acid. This is an oxidation on the aldehyde, right? Okay, right. So that's the only part that changed. So the only thing that we're going to do is we're going to do something to this. Okay. What do you think you'll do first with this guy? There's actually a reason why you can form that phosphoester. That is because instead of doing that, what you have is a deprotonated thiol. Okay. Quick question for you guys: how do you generate a deprotonated thiol? Okay, first of all, what amino acid has SH? Cysteine. Okay. All right, so you have a cysteine. Okay, so initially you have some kind of a cysteine group, and on the same enzyme you have a basic residue that can sort of pull it off, and the electron can go on to the sulfur. So you generate this deprotonated sulfur, okay, deprotonated thiol. And the deprotonated thiol now becomes a very good nucleophile, so it's going to attack here. Okay, so it's going to do that. Right. So instead of deprotonating, I don't know what is it about the alpha hydrogen that I really like. So it's going to do that, and you will form this tetrahedral intermediate. Okay, so you form this tetrahedral intermediate, right? Because somebody has to go, like that. Okay. So you first generate some deprotonated thiol. Now the S- is a very good nucleophile. So nucleophile is going to attack an electrophile, which is the carbonyl center, and the electron will pop up to the oxygen, forming a tetrahedral oxyanion intermediate like this. Okay, looking like that. And obviously the next thing that you want to do is this negative charge is going to pop back down. Okay, when it pop back down, you have two choices. Obviously you can choose to kick out the enzyme with the thiol. Okay, you can choose to kick that out. But if you do that, if you kick this guy out, then you restart it with, you then regenerate where you started from. Okay, so that's not good. So what you're going to do, turns out, is you're going to kick out this entire hydrogen as a hydride. Okay, so here is your hydride acceptor, which is called NAD. NAD initially looks like this, like that, like that. Okay, so the nitrogen is positively charged. Okay, so remember, whenever your nitrogen has 4 bonds, okay, it will be positively charged. Okay, just so you know. This is why it's called NAD plus a lot of times, because it has a positive charge on here. Okay, so this is NAD plus. Okay, this is NAD plus. Now, as the electrons from the oxygen collapse back down to form a carbonyl, the 2 electrons here with the hydrogen together they will move, okay, as a H minus, okay, this is called a hydride. This thing is called a hydride, so you're going to do a hydride transfer where the electron is going to attack this particular carbon on the NAD+, okay? Now, if you form a new bond with this particular carbon, now this carbon would have too many bonds, so then this carbon electron pop over here, okay? And this electron is going to pop onto the nitrogen. Okay? So at the end, what you generate is, let me erase this real quick, is your this thing is now NADH. Okay? So by NADH, here the H we sort of signifies as now it has a hydride on it. Okay, it has now hydrogen on there. So if you compare NAD and NADH, NAD has 3 double bonds, NAD has 3, NADH has only 2. Okay, so NADH is more reduced. Okay, and this guy just become oxidized. Okay, and this is now oxidized because instead of a hydrogen here in an aldehyde, now you have a thiol ester. Okay, so this thing, this particular thing is a thiol ester. Okay, now remember that thiol esters. Remember in our first lecture we said hydrolysis of thiol ester can release a large amount of energy. Why? Because the resulting acid has resonance stabilization. So the delta G is close to that of an ATP. Remember we said that? Okay, we did. So it turns out throughout evolution, what biology would then learn to do is instead of doing a hydrolysis to get an acid out of this and sort of waste that energy, what we're going to do is we're going to turn that into a phosphate because later on I can use that phosphate to produce ATP. Okay? So what happens, can I erase the NADH for real quick? Right? So what's going to happen is that you're going to have a phosphate here. I'm just going to write like this. Okay, phosphate here. This is inorganic phosphate. And inorganic phosphate, because it has so many oxygen on it, obviously one of the oxygen has a charge, and then it can attack here, pop up. Okay, you then generate your tetrahedral intermediate. Okay, we're good. Negative charge comes back down. This time the sulfur leaves, okay, the enzyme leaves, and then you're left with your carbonyl, O-phosphate, two OH, 3-phosphate. Okay, like that. Right? Right, so something like that. Right? So you can then turn an aldehyde into a phosphoester. Okay? And if you look at the screen over there, you see that the delta G is not very large. It's 6.3. Okay? So obviously the cell does not really favor the production of 1,3-bisphosphoglycerate, but not too bad, not too bad, okay? Obviously they don't like that because you now put a bunch of negative charge on the same molecule, okay? In terms of the 1,3-BPG, okay, this guy is 1,3-BPG, 1,3-bisphosphoglycerate, okay? 1,3-BPG. So 1,3-BPG has many charges because there are 2 charges on each phosphate, so you have a total of 4 charges. It's not going to be very happy. Oh yeah, and your enzyme, right? The enzyme S minus, right? It's going to like grab the proton from the base that deprotonated it. So just to complete a catalytic cycle. Next we have phosphoglycerate kinase. This is reaction 7. Reaction 7, phosphoglycerate. Okay. Glycerate is sort of, OH here, that's glycerate. Phosphoglycerate, it's just phosphorylated. Phosphoglycerate kinase, okay? This thing is kinase, okay? It's a kinase. But it's actually named kind of weird because it's named for the reverse reaction. So if you look at the screen over there, what you see is that we're using this reaction 1,3-bisphosphoglycerate plus ADP to give you 3-phosphoglycerate plus ATP, okay? So if it's called phosphoglycerate kinase, so it's actually named in this direction because it's the kinase acting on this phosphoglycerate, okay? So it's named for the reverse reaction. Don't ask me why, but that's just how it is, okay? A lot of times people do that, all right? Now, this guy is a kinase, okay? So essentially, it's going to be the reverse of hexokinase, kind of, okay? The mechanism that you learned previously. All right, so here you have like this, okay? So you have your 1,3-bisphosphoglycerate, okay, 1,3-BPG, and you have ADP here. I'm going to draw AMP, okay, and then O, 1P, okay, and phosphate. Okay? We'll draw it like that. And essentially what will happen is you're going to do water is going to attack here, and then this entire energy right here is going to transfer onto this phosphate, okay? So this guy is going to go to the phosphate. So, right, so it's the reverse of a kinase. Okay, so you take this and then react it with this particular phosphate, and at the end, what you get is here you liberate the phosphate. Now this becomes acid, and recall that acid has a very good resonance stabilization, okay? Resonance stabilization, so this is very stable, and you use that energy to sort of drive the formation of your AMP, 1-phosphate, 2-phosphate, okay? So this guy is ATP. Okay, so the mechanism is just the reverse as the first step. Okay, so look over your first step and then work backwards, and then you'll get this mechanism. Oh yeah, so there was actually a mistake that I made drawing the phosphoglycerate kinase. One was okay. So I'll just draw it out. So when I say, okay, basically, initially I said something about this minus attacking there. No. It's actually here, it's going to grab this guy and then like that, okay? So just make sure you correct your notes, okay? You're going to use the minus charge on the ADP to grab this phosphate such that the electrons can go to the oxygen because, this thing, I don't think it leaves. Okay, so just like that, okay? We're good? All right, so the next reaction is called phosphoglycerate mutase, I think. Okay, phosphoglycerate mutase. Reaction 8, okay? And this one is actually pretty interesting. You would think that a mutase is something very similar to an isomerase, but turns out it's not, okay? Turns out it's not, okay? This guy is going to become this, okay? So you're going to change the phosphate from 3 position to 2 position. So you're going to generate go from 3PG, 3-phosphoglycerate, and you're going to go to 2PG, 2-phosphoglycerate. Okay? And remember, glycerate is just 3 carbon, here OH, OH on here, OH here, and then acid. Okay, that's glycerate. Phosphoglycerate is where you have a phosphate on it. Okay? This mechanism is actually quite interesting because somewhere, okay, on the enzyme, you will have 2 residues. Okay? One of the residue is phosphorylated and one is not. Okay? And essentially what you'll do is you'll first phosphorylate this guy. And the way to phosphorylate that guy, you know, electrons here attack the phosphate, and phosphate electron donate here. Okay, so like that. Okay? You generate this intermediate. Okay? And then what you're going to do is basically take this phosphate and put it onto here. And you'll generate that, with the enzyme being like that. Okay? So you're just transferring phosphates. Okay? That's all you're doing. Transferring phosphates. Okay? Where 2 residues, one phosphorylated, one is not. The phosphorylated one is going to throw the phosphate onto the OH, the 2 OH here, and then you'll generate this intermediate where both carbon 2 and carbon 3 are phosphorylated, and then your enzyme dephosphorylated. But obviously it doesn't stop there because you have to somehow regenerate the enzyme. So the 3rd carbon phosphate is going to be transferred onto the enzyme. But what you'll notice is that your enzyme now switch the phosphate positions, and the enzyme will just go back to like that. Okay? And you're done. Here's a general question for you guys. This energy is a mutase. It's a, you know, you change the position of your phosphate, but why is the delta G like positive? Because your negative charges are too close. Make sense? Okay. All right. Reaction 9 is called enolase. Okay, and the name is obviously having something to do with the fact that you have an enol somewhere. Okay, so this reaction is also named by its reverse reaction where PEP is an enol, okay, and you are degrading the enol, okay, or just hydrolyzing the enol. So it's called enolase. Okay, so here you have what is this? 2PG, 2PG, and your final product is, okay, so that's the acid. Here is the O-phosphate. Okay, here's alkene. So you did a dehydration. Okay, so it kicked out water. You essentially kicked this out. In terms of this mechanism, now we actually have a use for the alpha proton, okay, or the alpha hydrogen. Your enzyme grabs this guy, okay, grabs that guy. This, okay, you can think of it as it go to form an enolate. Okay, you can do that. Actually, no, sorry. It doesn't really form an enolate. What it's going to do is when you pull this proton away, these two electrons is going to go somewhere, right? And where can it go? Okay, it can go to form a new bond here. or it can form a new bond here, or it's going to be on the carbon to form a carbanion. Okay. Now, in short, it's going to form a carbanion, but what it's going to do is it's going to go and form a new bond here. Okay? And the reason why we do that is because here it already has a lot of electrons, okay, because you have a negative charge here. Okay, so it doesn't make sense to draw more electrons towards the acid group, okay, because acid has already a lot of electrons here. So it's gonna go on this side, and then what you'll get is here, when you form a new bond here, okay, when you form a new bond here, and this is gonna go somewhere, okay, so turns out this bond will grab a proton, okay, and you can think of this proton the same as essentially this proton, okay, and the net result is just that, okay. So let's say you grab a H2O, okay. Let's say you grab a H2O and you kick out the water. Now you have OH minus here, right? OH minus, and you have enzyme B plus. OH minus, grab the plus, and then this becomes H2O and enzyme B. Okay, so you regenerate the enzyme. But this is essentially one step where you grab the proton or the hydrogen, you grab the alpha hydrogen, and then the electrons can form a new bond between carbon 2 and 3. And as you form this new bond between carbon 2 and 3, the hydroxyl group on C3 will then grab a proton and then leave. Okay? Maybe okay? All right, so this is enolase. And the last one is pyruvate kinase. So it's called pyruvate kinase. That means that it's an enzyme that can take pyruvate plus ATP to give you something else. But turns out this is not reversible, okay, because PP energy is very large. It generates ATP. So if you take ATP and you want to activate pyruvate, it does not just go reverse. This is what we'll talk about a little bit later. But this is a very thermodynamically favorable reaction. Okay, if you look at the screen, what you'll see is that the delta G is minus 31. Okay, so it's actually very thermodynamically favorable. Okay, now this reaction mechanism, I don't think I have to show you again. Right, it's just the reverse of a kinase reaction, where you take ADP and then you get the phosphate from it and you form ATP. Okay, but essentially what you'll get is you get rid of this phosphate to ADP. Now this becomes OH, okay? And OH, this is enol, and because enol is less stable than ketal, it's going to do a enol-ketal tautomerization, and it will form the ketal functional group. All right, so this is a summary of glycolysis. All right, the net summary is that we covered 10 reactions going from glucose to pyruvate, okay? Glucose to pyruvate. And in the payoff phase, so this is payoff phase, the lower half of glycolysis, you take 2 glyceraldehyde 3-phosphates and you generate 2 pyruvate. And in the process, you generate 4 ATP and 2 NADH. Okay? Now, subtract the 2 ATP that you used in the investment phase. This is the net reaction. Glucose gives you 2 pyruvate, 2 ATP, 2 NADH. Okay? Where NADH is electron, ATP is energy, and pyruvate is carbon. Okay, it's carbon metabolites. So we can use pyruvate to do other reactions. Okay.